Okay, so thanks for attending this this session. We have, as I said, we have 3 fantastic papers, and I will simply, without further delay, I would start presenting the first, introducing the first paper, which is Events Put into Context, EPIC. From presenter will be Marcus Dies, but it's a joint work with Bart Holmes and Will van der Aals. Marcus, the floor is yours. You can start whenever you want.
Thank you, Josep. I'll share my screen. It worked a minute ago. Let's see if it still works. Can you?
It works, Marcus. Perfect.
Perfect. Okay. Well, then I'll start. Okay. Well, hello everybody, and welcome to this presentation. My name is Marcus Dies, and Josep already introduced us. So I will go directly into my presentation. So, the title of our work is Events Put into Context. So why did we choose this title? Well, in many processes, events occur that potentially influence the process execution, but are not necessarily part of the control flow or the design process. So examples are customers who call during a claim handling process, lab tests in a hospital care process, but you can also think of warning or error messages during software execution. And what we want to be able to analyze the impact of such events on the process. So our question is, how should we deal with these events that are part of the process, but are not part of the control flow? So now, some of these types of events also have a negative impact on the result of discovery algorithms. And to give an example, here's a process model and an event log with 1387 traces that are 100% fitting. And the process model can also fully be rediscovered using these traces. So now we add 4 traces with events X, Y, and Z mixed within the fitting trace that are not part of the process control flow, but are still related to the process. When we apply a discovery algorithm, the results look like this. And so, which shows that the structure of the process can no longer be rediscovered by only adding these 4 traces to the event log. So another problem that occurs when we want to analyze and visualize these types of events. So we tried some techniques. One of them was the artifact-centric approach using the CSM miner in PROM, but that did not really work because these types of events are not connected to each other. And when we would select a control flow transition from the process on the right side of the slide, all the context-related transitions would get selected in the not control flow related process shown on the left side of the screen. So everything is connected with each other. Well, to still get some insight in when these events occur, we used the multi-perspective process explorer in PROM, and we edited the process model to catch these events at every state of the process, which is shown here in the red colored transitions. So we added an extra transition to every place in the battery net, and when a non-control flow event occurs, anytime during the process, it's captured in one of these transitions. But this is also not really satisfactory because actually it's a lot of work to interpret the results of this. And when we have multiple types of these events, we would need to edit process model again and again and again. So this leads us to the objectives of our approach. And what we would like is to be able to use all events during our analysis, whether it's a discovery or any other type of analysis. But we want to avoid that events disturb the results. And we also want to visualize these events that are related to the process but are not part of the control flow. So, and to do both, we introduced the concept of context events. So I will show you now how we identify these context events and how we visualize the context. So we have a two-step approach. We start with an event log and a process model, which can be discovered or hand-drawn. So, and we use the concept of alignments to combine both, and we obtain an extended alignment, which is an alignment with some extras. I'll come back to that later. And this alignment together with the process model is then used to visualize the context. So how do we do this? Let's start with the first step, identifying the context. So we start with an event log and we identify context events. And up until now, this is a manual step executed by, well, a process stakeholder. And we technically support this by adding the event type property to every event in the event log. We give it a default value of control flow, and then the user can identify events that have a different type, like call or lab test. So this produces an extended log, which together with the process model is used to identify context moves in an alignment. So to create an alignment, we use the process model and the extended event log. And we show one case from the extended event log, where event E2 with activity label X is a context event. So this event has event type context. And we create an alignment for this case using the standard techniques. And event E2 becomes move M3 in the alignment, which is also, it's a log move. Which actually all context moves will become in an alignment. So, similar to events, we add the move type property to alignment moves. Since event E2 is a context event, move 3 becomes a context move. So move M3 is the context move. So this is how we identify context within event logs and alignments and create an extended alignment. So next we want to visualize this context using the extended alignment and the process model. And well, visualizing context has again some sub-steps. The first is that we enrich the context moves with some additional information. And next we map the context moves to the process model. And finally, we visualize the results using the process model and the extended alignment. So the first step, which is enriching the context moves. So we want to plot context moves on PetriNet edges because, we chose edges because both transitions and places are already in use to visualize other types of deviations between the log and the model. So to do this, we need the preceding and succeeding control flow moves for every context move, because these are the links to a process model. So we start again with our extended alignment, including the context move M3. And next we find that move M2 is the preceding move with move type control flow, and M4 is the succeeding move with move type control flow. So when the directly preceding move is also, could be also another context move, we would select the control move that precedes that context move. So, and when there is no preceding or succeeding control move, we register an empty move. So this is how we add information about the preceding and the succeeding control flow move to every context move. And that's which is needed to able to map the context move to a process model. So next we will do this mapping. Again, we use the enriched context move with the preceding control flow move and the succeeding control flow move. From the transition of the predecessor, we select all outgoing edges. And in this case, it is only one edge from transition T4 to place P3. We can also visualize this on the process model. Next, we select all incoming edges of the transition of the successor, which in our case is the edge from place P2 to transition T5, which we can also visualize. So this is actually, it's a very simple process, but this is how we map the context move to the edges of a PetriNet model. So now let's look at the effect of this way of visualizing context when we do a discovery analysis. So we use the same process model and event log as shown before. Well, and has been shown, adding 4 traces with X4 events leads to quite a messy discovery result. But when we do not use this context, when we do not use the context events in the discovery, but only visualize them afterwards, we actually can rediscover our original process model, which is shown in the top left, without any of the previous disturbances. And we can also see where in the process model the context events are localized. So this can give insights in where these types of events may influence the process. And we also have an example of this in our paper using the sepsis log. But now let's turn to one of our case studies to see our approach with a real-life data set. So we use the unemployment benefits claim process, which is executed by the Dutch Social Security Institute, UWV. And when you become unemployed in the Netherlands, you can receive benefits, but first you need to file a claim. And based on your situation, your claim is either accepted or rejected. And before the decision is made, extra information can also be requested. And this can be done by sending a letter to the customer or by calling the customer. And before, during, and after this whole process, customers can also contact a call center with questions related to their claim. And so the question that we want to answer for this case study is, when and where in the process do customers call the most? So let's see what we end up with. So we used an event log with 10,000 cases and roughly 70,000 events, of which 4,000 are call events, so calls to the call center. Our approach is also fully implemented in PROM. So the next pictures that I will show you are actually created with PROM. We first actually created a visual, which we call the process heat map, which is based on the absolute frequency of the calls. And the edges that are colored red have context moves associated to them. So you can see that they're everywhere. And the thickness of the edge indicates the frequency. So how the thicker the edge, the more context events are associated to the edge. And we also see that now that most of these calls are actually situated between the claim decision and the acceptance letter. And we did some more investigation, and what we know is that most of the claims are actually accepted. So it's not so strange that we find most calls there. And they're also related to the question of the customer when they can receive their first payment of the benefits. So, but we can also look in a different way to this process in a more using the relative frequency. So then we divide the number of calls by the number of customers, and we get actually a different image. And then still the customers call between the claim decision and the acceptance letter, but now we can also see that after a letter is sent to ask for information, for additional information, relatively a lot of customers contact the call center. And apparently something is not so clear in this point of the process. And their questions turn out to be also related to the type of information that is requested, but also that they cannot answer on time. Also about, we're also inquiring whether whether UWV actually received the information that they sent. So everything is happening there. So these are actually valuable insights to improve specifically this part of the process. Well, to conclude, we introduced context events. We have shown how using context events can help in getting a better discovery results, avoiding disturbances. And we have shown how we can visualize non-control flow events in relation to a process model. And as future work, we want to actually identify these types of events in a more automatic way or semi-automatic way. And we know that there's already quite some research on this topic. At the moment, we can only visualize all types of context events in only one view. And we want to be able to distinguish between different context types. Finally, we also want to be able to plot context periods, so we can show, for example, the load in the process or customer sentiments, for example. So this concludes this presentation. Thank you for your attention.
Thanks very much, Marcus. Well done, perfect timing, and very nice work. So I open the floor now for possible questions that you might have. So you just simply have to ask in the Q&A, and I would simply allow you to talk. So is there any questions from the audience?
Let's see if I actually can see the Q&A myself or not.
Well, I can start with one. Maybe it's a warming up for you.
Right.
I think this is extremely sensitive to the way you compute alignments. So, for instance, when you compute alignments, you can get these context moves somewhere or the other, and then that will influence where you put these heat maps, these edges after that. So, I was wondering if you have evaluated, for instance, not using one optimal, but maybe a subset of the optimal alignment, so to have more confidence on where you put these red heat maps. Did you experience that?
No, we did not do that, but we're aware of this problem, and I think using maybe when there are multiple alignments, or maybe multiple alignments that are closely related, maybe we should do something with that. But one of the things that we did take into account is that, for example, when you have an alignment and you have a model move before or after a context move, well, that's also something that's that this decreases the certainty that a context event has occurred in this specific place in the process model. So we, in our paper, there's also something about we use certainty, and also you can actually see it in the picture that I just showed. That maybe I can even show it. You can also, next to the thickness of the arrow, you can also see the intensity of the color. So how the more intense the color, the more certain we are that things are happening in that specific spot.
That's good. That's good.
Yeah. So
let me just give the floor to also Artem. Artem, you can talk.
Thank you, Joseph. Thank you, Marcus. Very nice presentation. I understood the whole mechanics of the approach, like how algorithmically everything works. But also, I mean, maybe extending the comment from Joseph, I'm really curious where this context events information comes. Maybe can you at least give some idea, because it really feels like it depends a lot on which events are tagged as context events, and also maybe as a comment, because this very much reminded me of our work also with Will from 2017 on repair, where we also used similar, very similar, well, actually the same running example even from Will, right? So, and there we were trying to keep it by keeping the structure of the model, which is exactly the same, trying to fit the deviation right in a minimal possible way, kind of looks like what you're trying to achieve with your visualizations as well. So maybe that's just, I just briefly looked at the paper, you didn't cite it or didn't look into that related work. No. So maybe that can be related, but also this context event. So maybe you can comment, so because the guess or decision which events are context event then predetermines the whole approach. So this is a bit vague.
Please, Marcus, go fast because we have a couple of questions that I also.
Sorry.
Yeah, so if is your question, where do they come from, or how do we identify them?
Yes.
Okay, but for now it's a manual task, this idea also came from my company UWV. So and there we have the problem of these people calling us, and well, fortunately we have we can identify these customers by their social security number, so we can connect them to actually every process we're executing. So they're just coming from our data. So we the whole idea came from that.
Okay, let me just move and allow, maybe you can talk offline because it's interesting. Thomas, can you please make your question? But I think you are mute, Thomas. Sorry. Now you.
Okay, so now you hear me?
Yeah. Thomas? I cannot hear Thomas.
We just heard him, but now he's gone.
Thomas, can you try again? Okay, Thomas, can you? Okay, let's move to Will and let's see whether Thomas can then. Will.
Oh, Thomas. Yeah.
Audio. Now I should it should work. You hear me now?
Yeah, now it's
I'm sorry for the confusion. I missed to press that button over the other side, so I tried to. Okay.
But fast one, please, Thomas, because we are a bit.
Yeah. So thanks for the rich work and the great talk to present it. I have some different question which you did not discuss in the paper, but I'm curious about that. So how is the efficiency? So it's a good thing to bring in this context, as I learned here, and does it eat up a lot of resources in terms of efficiency, or does it help to be more efficient in finding some of the patterns faster? So I assume it's more time consuming, but maybe there are interesting other insights.
Well, actually, we did not really focus on efficiency, more on functionality, I must say, and we completely rely on alignments. So we're as efficient as the most efficient alignment algorithm that's out there. But we had some ideas also about using different techniques.
Thomas, excuse me, but I want to pass the floor to Will before going to the next talk. Will, can you do a very, very, very fast one?
Yeah, that's very difficult because many interesting things were raised. So of course there is a strong relationship with repair, to go back to Artem's question. Yeah. But the goal is not to change the model. The goal is to, so for example, if you look at the work with Artem, that the goal is to change the model with the least number of added changes and as close as possible to the data. One should realize that these context events can be super frequent, but you still do not want to put them in the model because they would just blur the image. So there are relationships, but also differences. To come back to your question, Joseph, and I think also to the last question about efficiency, I think in principle, if you have removed the context events temporarily, you can in principle just focus on the traces that are perfectly fitting. Because if they are not perfectly fitting, you get these arbitrary things. So I think you could make this idea super efficient by just considering fitting traces for the things that remove after removing all context events. And then you can deterministically attach them to the places that are in between these synchronous events. So I think this is a first step, but I think both in terms of efficiency and diagnostics, this could be fast and also deterministic in some sense.
That's very interesting.
Okay.
Yeah. So let's move on. Thanks very much to Marcus for the nice presentation and the audience for this nice discussion. But we need to move on a bit. We go to the next speaker, which is Marwa Eleoch. And can you please, Marcus, stop sharing and let. Good. So the next paper is is presented by Marwa. It's a joint work with several other authors, and the title of the work is Discovering Activity Actors' Perspective Based on Speech Act Detection from Email. So Marwa, the floor is yours.
Okay, thank you, Joseph. And hi, everyone. So I'm Marwa Eleoch, and welcome to this presentation where I will talk about our paper whose contributors are coming from Orange Labs, Telecom Sud Paris, and the Lebanese University. So first, I will illustrate the general context of our work. So our work is inscribed here in the context of discovering business processes from emails, since emails are nowadays widely used by employees to execute their daily business tasks. And due to the unstructured nature here of emails, we need a step to convert it into a structured format compatible with the task of discovering business process knowledge. However, this knowledge is most often limited to activity perspective, most often visualized in the form of business process models. And actually, there are some additional perspectives that could give more insights about business processes, such as here activity actor perspective that defines the set of actors that could intervene at the stage of execution of each activity. So in our work, we have been focused on discovering such kind of activity actor perspective. So in this context, the first one of question that could be asked is what kind of additional information that emails could provide comparing to traditional event logs provided by information systems supporting business process execution. So actually, such kind of event logs provides only the trace of activity performers or tasks performers of each sub process in the case where activity is implemented in the form of sub process in an information system. But in reality, several actors could intervene for performing an activity with different here contribution types and also outside the information system. And these contribution types do not necessarily correspond to performing the activity, but could vary from, for example, requesting the execution of the activity, requesting some useful information, or simply observing how the activity is executed without doing concrete action. So here in other side, in the case of emails, senders usually introduce activities using specific speech acts that could reflect their actual contribution in performing the activity. Taking this example of email retrieved from the public data set and run here, the sender introduces at least 3 activities. So the level of the first activity, he says, for example, here for mandate, is necessary that we say the following for Frontera. So here, the sender introduces an activity of setting power with a speech act of intention, which could reflect his contribution of planning the execution of this activity. The same thing for the second activity of buying electricity power. And for the third activity here, the sender says, also please make sure that the premiums up and down are input as $50 and $40 respectively. So here, the sender introduces an activity of checking some prices with a speech act of request here, and this reflects his contribution of requesting the execution of this activity. So based on this kind of additional information that could be provided by emails, so our main proposition was first to exploit the textual content of emails to identify actors' contributions in terms of speech act. And here I have identified 6 types of contributions, which are execution, request, planning, request some useful information, observation. And our second contribution was to define activity actor perspective according to these 3 notions. So the first notion corresponds to the set of actors that perform activities or contribute to perform activities, and that could be retrieved or deduced from the information of sender receivers of activity-related emails. The second notion corresponds to actors groups, where each group corresponds to the set of actors that frequently interchange activity-related emails. And the final notion corresponds to actor contributions, where each actor will be represented by the distribution of his or her contribution. So to discover such kind of actor perspective according to what we have defined, so we have proposed an approach composed of 3 main phases. So in the first phase, we have we have done some pre-processing steps on emails main bodies. And the second phase, or the goal of the second phase, was to convert email logs data into structured event logs compatible with our defined actor perspective. And each event in this event logs corresponds to the occurrence of one activity in one email. And finally, in the third phase, the aim is to exploit this structured event logs to discover actor perspective of each activity. So in Untitled, I will give more details about the second and third phase. So I begin here by the second phase. So to construct or generate structured event logs from emails, here it is mainly about detecting its main entities. So first we begin our side by detecting activities, occurrences, and emails. And here we need to know the set of activities that we target in these pre-processed emails. That's why here we were based mainly on exploiting our results obtained from our previous works accepted this year in the PM forum, where we have introduced an approach for discovering activities from emails based on pattern discovery approach. And here we have defined an activity as the composition of an activity name, such as here purchase power, and the set of related business data used and generated, such as here the number, the quantity, the price, and the hour number of the related trade. And each activity component was discovered in the form of set of patterns forming kind of semantic characterization, allowing each detection later emails with more flexibility, even when using, for example, different words, sharing the same meaning or sharing the same context of use. And using these patterns, we were able to detect activity occurrences in emails while extracting the exact position of appearance and also the sentences where they have occurred. Then we were able to extract some grammatical local features of each occurred activity and some textual indicators that could reflect the real doer of the activity, which could be, for example, here, some personal pronouns or the name of some organizations or persons. And finally, we have predicted the speech acts of each activity occurrence. And here we have defined 4 types of speech acts, which are information, request information, and intention. And for this purpose, to this end, to ensure such kind of prediction, we have proposed 2 kind of methods. In the first method, we have integrated some supervised learning algorithms. So here for deducing the learning features of each occurred activity, we were based, or we have deduced them for the grammatical features of words appearing in the same sentence where the activity occurs. And as numeric representation of these learning features, we have used the distance in terms of difference of position of appearance that separate each feature from activity verb. Our second method is based on defining set of rules that we have summarized in the form of decision tree. And the idea here was to define speech act on the basis of some specification of the sentence where the activity or the occurred activity has appeared, and also the tense of the activity verb. For example, by saying if the question or the sentence where the activity was occurred is a question, so the speech act would be a request or request affirmation act. Or if the tense of the activity verb is in past, so the speech act will be or would be an affirmation. And finally, if the activity verb is in future tense, so the speech act would be an intention. Now, after obtaining that structured event logs, we come to the third phase where the aim will be to exploit the structured information to discover the actor perspective of each activity. So first we project our event logs on each name of each activity to obtain the related sublogs. And when starting from an event sublog of an activity, the first step will be to deduce the related actors and the related actor groups from the information of sender receivers of activity related email. Then the second step will be to identify actors reacting on each event. Here, for example, by identifying actors that reply or forward event related emails, or that send other independent emails containing relevant business data values. And the third step will identify potential actors' contributions at each event. And here we do such identification first by deducing it directly from the information of event speech acts. For example, by saying if the speech act is an information, so the contribution will be an information also. And if the speech act is an intention, so the contribution will be a planning. And second, we deduce this kind of contributions and directly from speech act information by integrating other kind of information such as actor indicators and actors reacting on each event. For example, by saying if the speech act is an information and actors indicator correspond to the first person pronoun, so the sender contribution will be an execution. And finally, here we determine the distribution of each actor contributions by applying some operation of aggregations on the overall contributions defined in the third phase. And what remains here is the identification of the observation contribution of actors. So we assign this kind of contribution to each actor that receives activity-related emails with copy status without doing or without having execution contribution. Now, to evaluate our approach, we have been mainly based on emails retrieved from the public datasets and these emails concern the emails of 9 employees having different organizational and business roles. And after applying our algorithm that discover activities, we have obtained a total number of 106 different activities, having around 2,030 or 2,300 occurrences through the analyzed emails. And to evaluate our step where we have predicted the speech act of the occurred activities and which presents actually a key step in our approach, we have selected a sample of 937 occurrences of activities and we have annotated them in terms of their speech act. Then for our supervised method, we have tested some existing learning algorithm or supervised learning algorithm, which are supervector, machine, random forest, and decision tree. And we have used F1 score metric to compare the predicted speech act with the annotated ones. And here the different values that we have obtained that vary from 0.79 and 0.91. And as the higher value was obtained for our rules-based methods, so we have adopted its result in what remains in our approach. Now, finally, we have studied the variation of the accuracy of speech act prediction, activity detection per activity, and also per employee. Here to prove the good performances of the sublogs that we have obtained for each activity. Now, finally, to visualize the active perspective of each activity, we have proposed a visualization composed of 3 main graphs. In the first graph, we have illustrated the different interactions that could be made between senders and the receivers. So here, each directed edge reflects the number of emails that was sent by sender to a set of receivers but with a specific speech act, and this speech act is reflected by the color of the directed edge. For example, here the green color reflects the information speech act, and the orange color reflects the request execution speech act. And here the dashed line, or each dashed line, regroups the set of nodes of actors that corresponds or belongs to the same actor groups. In the second graph, we have illustrated the different interactions that could be made between senders. For example, here this employee only sent information about execution, while he receives either request or intention about execution. And finally, in this third graph, we have resumed the different distribution of senders' contributions. For example, this employee made 75% of requests and 25% of planning. Now, finally, to conclude, during our work, we have discovered active perspective activities based on actors' contributions used from the speech act that we could detect from emails. Also, we have validated our approach using emails from the public dataset Enron. And we have proposed the visualization of active perspective of each activity. And finally, we have publicly here shared our results for reproducibility reasons. In terms of perspective, so we plan to do further analysis to study if our main assumption that we have adopted in our work remain valid if while varying employees are still, and also we aim to extend our results to obtain active perspective at business process level. Now, to this end, thank you for your attention.
Thanks, Marwa. Very nice and very complete and very nice work. Now it's time. We have few time for questions. We have a couple of them. So first is for Esribedi. Can you say your work, your question? Esribedi, I think you are muted. Okay. So I think you are talking, but you are muted. Okay, let's switch to Will, and then we can move to Will. Can you talk?
Yeah, I can talk. Yeah, so thanks for the presentation. Also in the related work, you refer to to the work that I did with Nikolav like 15 years ago on also mining exactly the same data set. You focus very much on activities and the social network, and kind of already in the beginning you kind of say, okay, I don't focus on the case notion. And perhaps you can add some words to that, specifically because we are in a process mining conference. It would be interesting to hear your ideas about this. That would be the first part of the question. The second part of the question would be, having done this analysis myself on this data set, I very much had the feeling that it would be very valuable to combine email information with information from, let's say, structured information systems like SAP, because in the emails there are often identifiers that refer to, let's say, real instances in these enterprise systems. So the question is, can you comment on this, both about dropping the case notion and whether combining this with, for example, SAP data would be valuable?
Yes, thank you for your two questions. Now, for the first question about cases, actually, what we have done in our work is to try to illustrate actor perspective, the global actor perspective of each activity. Now, we didn't handle the case because in emails, there are some difficulties to identify the information that could identify uniquely the information of instance. And sometimes such information is absent in emails because employees, when writing their emails, they do not integrate or mention the exact notion of instance. So we have chosen to perhaps discover the global interaction that could be made for one activity, not for each instance. But this kind of answers, I think that it could be provided when integrating the event logs provided by information system supporting process execution, which corresponds to your second question. So I think that discovering activity actor perspective with case perspective, with case notion will be feasible or more feasible. I don't know, will be more feasible if we do such combination.
Yeah, so I'm asking the question because like it would be interesting to know, like if there is a bottleneck in a process or non-compliance, to relate that to the resource or the user perspective. And that is now a bit difficult because you see the interactions and you have no idea whether, I don't know, the exchange of these emails was the cause of a bottleneck in a process or something like that. And I think, but I think we agree that it would be helpful to combine this with real event data. Yep.
Yes, also I think that the information of case or instance would or give would able us to discover the local or life cycle of each activity. For example, here we say we define for speech act request execution, then execution, and request time information. So this kind of speech act could form local life cycle of each activity. So if we are able to identify the exact information of instance, so we could do further analysis that cover even the life cycle of activities.
So I would suggest to stop here because we need to move on. So thanks a lot for the discussion and thanks to Marwa especially for the nice talk. We need to move on to the next. So Marwa, can you stop sharing?
Okay.
And, the next speaker, the last speaker of this session today is Ahmed Abad with a very nice paper also called Process Mining over Unordered Streams. Ahmed, can you put your presentation and start, please?
Yes.
This is while you do it. This is a joint work with Matthias Weilich and Sheriff Sacker.
Yeah, thank you.
Thanks.
Yeah, you can see now my screen and hear me. Thank you. Yeah, so thank you for the introduction. Welcome to my talk about process mining over unordered event streams. So if we start with an offline process mining context, and if we look at the nature of the data, which is basically the event log, which is could be large, but it's finite, and we can have the freedom to do any sort of pre-processing on this log in order to put it into the shape suitable for the respective analysis. And if we look at the nature of processing, like using a discovery or conformance or whatever the task, such algorithms have no restrictions on the way they access the data, how many times they need to access the data, and generally there is no restriction on more normal constraints like for latency or like memory constraints. Also, regarding the output observation, we can only observe this output at the end of the processing, being it the discovery or conformance task. But recently, we need to do these tasks in an online setting, maybe because we need to have better insights, or maybe we need to account for or detect deviations and start taking counter actions to prevent further deviation or to put back the process in the correct path of execution. So looking at this nature of streaming, like online process mining, meaning like we receive the data in streams. So we have now some restrictions or some constraints for these processing techniques. So that first of all, that we have an event stream rather than an event log, meaning that we can receive the data in batches or one by one, and this data could be infinite. And in the meantime, we need to have some sort of an incremental computation paradigm. So moving to an online setting, we need to get some updates, maybe with higher frequency than an offline setting. And so our algorithms need to be incremental. We need to embrace data structure or intermediate representation that support incremental updates. And of course, we will have some sort of continuous updates. And in a streaming context, we have further constraints, basically maybe on the limited processing space or processing memory. And in the literature of process mining, there have been approaches that have addressed these different techniques for discovery and for conformance checking. And the focus of this paper is on handling some sort of stream imperfections. And imperfections in stream could be that there could be delays in the events. The events can arrive in bursts, like suddenly the arrival rate changes, and also they can arrive out of order. And to see this, the effect of out of orderness, let's assume that these three events from the same case have been generated in this order, which is called the event time. So this is the generation time of the data. And in an in-order arrival, if things are perfect, these data or these events at the conformance or the process mining observer will be observed in the same order. So we first observe event A. So if we're maybe maintaining some intermediate representation for a discovery like a directly follows graph, we can construct the graph incrementally in a way that reflects the same order of arrival of the events. And it's also the same order of generation. And if we are in an alignment context, also we can derive a correct alignment to the model. But what if the data are coming out of order? Meaning now we again start or we observe A first, but then we next observe C instead of observing B. So if there are no precautions made to make these corrections, we will start like in a false way, derive wrong representation or derive wrong or maintain wrong artifacts. Like we can derive a wrong direct follows graph, and we can end up with indicating that this is there is like a deviation between the log or the trace and the process model. So in this paper, we are addressing this problem of how to account for an order or like out of order arrival, so to say. And in literature of stream processing, there are basically three techniques for handling such out of order arrival. Either by buffering, which is the simplest, which means that you will wait for a bit of time, like for a time window for some time, and then you keep collecting the events. And once the window closes, you simply reorder those events to account for any out of order arrival in this window, and then simply send these events in the right order downstream to the respective operator, which could be a mining operator in our case. The second approach is the speculative, which actually is an optimistic approach, which assumes that everything is fine and in order arrival is assumed. So it immediately, with the arrival of a new event, it immediately increments or updates the model or updates the artifact and sends this downstream. And only in the case of observing an out of order arrival, then it has to, like what we call retract or like undo, send some updates, some corrections downstream to the next operator. And the last one is punctuations, which is a special case which assumes that there is some ordering guarantees in the underlying stream. And the rest of this talk, I will talk about the buffering and speculative techniques as they are generic enough to employ. So let's assume here that in this timeline, we have the events that should have are generated and could have been arrived in the correct order. So this is like an in-order arrival. But what if they are starting to arrive out of order? So using a windowing approach or a buffer, with the first buffer, we just observe this event and we construct the directly follows graph. And then within the next window, B arrives out of order, but still within the same window. So we are able to reconstruct and fix or reorder things and still compute a correct DFG here. And also continuing again, A for case 2 arrives out of order, but we are still able to handle it. And we update the weights of the graph and so on and so forth. Here in this window, again, C arrives out of order. And for case 2, C now is the most recent event received. And by the end of each window, when we compute and send the update of the direct force graph, we immediately get rid of the context for the respective case. So in this case, when D arrives in the next window, it arrives too late. So this leads to that D will be dropped because we have no longer context for this case and we cannot know what was before it. We know C, but we don't know what's before it. And then if we compare this computed DFG to the one that should have been computed if everything arrived in order, we can see that there are some differences here, that the weights of the edges and some edges and even some nodes are missing. So if we repeat this again with a larger window, we can see here that, okay, we can account for almost all out of order arrival, even the late one, and we can compute a DFG that is identical to the in order arrival. But the problem here, of course, is that we will have higher latency because we are going to make the window wider, meaning that every 60 minutes we will get an update to the graph. Moving to the speculative handler, this one works one by one and it maintains like a per case DFG and what we call a change DFG and the global DFG, which is consolidates the updates from the different running cases. And now if we receive 1A, we immediately construct this case DFG and the change is the same node because the graph before it was empty, and then this is the case for the global DFG because this is the first case we received. And now we can observe here that 1C was received, and we can observe looking at the upper timeline that 1B will arrive out of order. So we can deduce here this graph that we observed A followed by C and so on. And now once 1B arrives out of order, the case DFG is updated because we know the timestamps of the events and we can reorder them, and we can, comparing to the previous case DFG, we can deduce here the change. And as you can see in the change, there is this negative weight which we call a retraction edge, meaning that this was a wrong computation, this was a wrong relation, we need to lower this frequency in the global DFG by this way. And if we play it fast forward to the last event, we can observe again this case here with the case of arrival of 2D. And at the end, the global DFG for the processing of this prefix of the stream, we can see that we obtain an identical graph for the case that events have arrived in order. So in our evaluation, we wanted to understand how buffering and speculative processing perform on a different level of out-of-order arrival, and specifically for the buffering technique, what is the effect of the buffer size, which you can see as like I have a parameter here. And for this, we have used both synthetic and real-life logs. And we have set up our ground truth in the form that we passed the event from the log as a stream, which is ordered, so everything is in order, to both the buffered and speculative handlers, and we have recorded the computed DFG after each step respectively, after each arrival of event in a speculative case, and after each window in the buffered case. And then we introduced several degrees of out-of-orderness to the stream or to the log, 10%, 20%, etc. And then with these unordered events, we have passed them again to the buffered handler, the speculative handler, and we have passed them again to those handlers, but without enforcing any order. So as if the technique is like order, out of order, unaware. And in our evaluation, when we compared the average accuracy, as you can see in general, increasing the window size leads to better accuracy for the window or for the computed DFGs, even with the increase of the out-of-orderness percentage. But overall, the speculative handler performs in general much better than the windowing, because as you can imagine that it does not drop any events, while in the windowing approach events might be dropped, and this will cause a degradation in the accuracy. Also, we have compared to see like the effect of reordering or out of order awareness against unawareness of the out of order. And as you can see in this figure, we have compared the window of 60 minutes. And as you can see here in the order aware, like those top lines here, it almost converges to one, to accuracy of 1, even with higher out of orderness percentages, whereas in the out of order unaware techniques, the accuracy drops severely to around like 0.3. Same case is for the speculative approach, but which is actually reaches the accuracy of 1 at the end of the processing. For the real life logs, we can see similar patterns here that, of course, in general, the speculative and windowing or the buffering approach perform much better than the order unaware. But you might ask here that why, for example, for the speculative approach, it does not converge to 1 at the end. And this is due to the granularity of the timestamps or the accuracy of the timestamp log, because we observe several events in the log that have the same timestamp. So when you are reordering them, they are indistinguishable, and then for the approach, they could be false negative as they are arriving out of order. So to conclude, we have introduced 2 approaches to handle out of order arrival within streams, which is a practical issue that should be considered when really dealing with event streams, especially that coming from distributed sources. And in the buffered handler, it's simple to implement, has no more effect on, like, it can work with any whatever mining operator or mining task afterward, because simply it reorders the events and sends them downstream. But of course, it comes with higher latency, depending on the window size. Whereas the speculative handler can give you much more accurate and much more frequent updates, but it's CPU intensive because of the recomputations, and it would require maintaining much larger state. And in addition, it would require implementing the retraction logic with respect to the mining task. In the future work, we would intend to build a hybrid approach that tries to balance between the computation overhead, memory, latency, and accuracy of out-of-order handling for process mining. This concludes my talk. Thank you very much, and I'm looking forward to your questions.
Thanks very much, Ahmed. Very well, deployed. Very nice presentation. Very interesting, insightful. So we have a question. We have a few time for questions. We have a question from the questions and answering. So I will simply, for the sake of simplicity, to tell it. This is from Bart Holmes. He's asking, in the buffered handler, you describe how you are able to handle out of order events within a time window. What is the oracle that tells you what the correct order should be? And if such oracle exists, why do you need the buffer?
So basically, this window works like in the time of the what we call the processing time of the operator, which is like receiving or observing the events. And simply each event comes with a timestamp built in it. So at least we know like these are the three basic elements of any event, like the case ID, the activity, and the timestamp. And so basically, when we observe a new event, we can compare its event time, its built-in timestamp to the other ones, and with this we can figure out that there is an out of order that has occurred. Yeah.
But this is quite a heuristic, I would say then.
The heuristic could be like the choice of the window size, like the window length. How long would you wait until you collect the date, like 30 minutes, 1 second, whatever. Like, but to determine that the two events are out of order simply because you have both, like the timestamp when it arrived at your system and the timestamp when it was generated. And by comparing those, you can figure out that there is an out of order arrival.
And just a small question: would you consider, for instance, this new adaptive windows that adapt the window so that in this case would be if you see that they are arriving a lot of out of order, then you would maybe shrink or widen?
Exactly. This is basically one of the directions for the future, which is the hybrid approach. Also, that if things are arriving out of order with high frequency, then it's wise that you wait longer because you don't want to miss those. And if things are arriving in order, then maybe you want to shorten the window and give updates more frequently.
Let me just ask a question by Dirk Fallan. Can you comment on which use case would most benefit here? Often, business process events do not arrive within a few seconds, but have large times in between. So,
yeah, this is a good question, but yeah, in this case, I can see that mainly the speculative handler would work because if you are waiting for like maybe a window of even 1 hour, so several windows will go on without an update. So in this case, I would see the speculative handler would work. But the use case here, you can think of any like process that requires execution of different distributed information system, like a logistics process or something where you cannot have a global clock synchronizing all the events across different systems. So yeah, this is what I can think of. And in this specific case here, when events are arriving at like very slow, so to say, I would say that the speculative handler here would be much better fit than the window-based.
But definitely, this is a research line that you are opening. I think there would be more papers, more work on this. I'm sure about that. So nice work again. So with this, I conclude this session today. We are only 4 minutes late, which is not that bad. I think the discussions were quite interesting. I would like to congratulate again to the speakers and also the collaborators of the speakers, which make this work possible. And thanks a lot. You can put your camera just to finish. Marwa, don't be shy. Are you there? No, maybe she's not there anymore.
Yes, I'm.
Oh, thank you. So with this, I conclude this session. Enjoy the rest of the conference. That's all for today. Thanks a lot.